Giovanni Valsecchi and Marta Ceccaroni appeared on Celestial Mechanics last year. And well, my presentation is divided in two parts. In the first one, I will give the motivations for which the study is interesting. And whereas in the second part, I will state our results. Well, so to start, I have to say a few words about the line of variations, especially for those who are not familiar with this tool. Well, this line of variations is a smooth curve in the orbital element space, and it is used to represent the line of maximum uncertainty of an asteroid confidence region. So, well, to help you understand this concept, you may imagine to be in the linear approximation for which the uncertainty of the asteroid is simply represented by an ellipsoid. And when I say line of maximum uncertainty, in this case, I'm simply referring to the major axis of this ellipsoid. But of course, in the general case, the uncertainty is not an ellipsoid, but it's kind of a distorted ellipsoid. And thus, you can easily imagine the corresponding distorted semi-major axis. And that's what I call line of maximum uncertainty in general. And this is roughly the line of variations. Well, when an asteroid has been designated, in the vast majority of cases, the confidence region is thin and is also elongated mostly in one direction. And this is why this line is a good representation of the entire region. So we are replacing a six-dimensional region with a one-dimensional manifold, which is, of course, simpler and to treat and also more feasible for computations. Well, why do we want to represent the uncertainty of an asteroid? Well, the reason is that we would like to make predictions, and one of the most important ones is the hazard prediction for asteroids. And indeed, the Love method is at the basis of the two currently available impact monitoring systems worldwide. One is GLOMON2 here, University of Pisa and Space Disk, and the other one is Sentry at JPL, of course. Well, and this also explains the second part of my title, so why we are interested in studying how the line of variations evolve at a close encounter. And this is why, well, to explain also this part in a little bit more detail, when you have an impact possibility of an asteroid with the Earth, what you essentially have is a small portion of the line of variation which is impacting at some date. Well, here there are two possibilities. Either this small portion has a direct impact and, well, that's it, I have nothing to say here, or that small portion had a previous close approach and it passes through a resonance circle. So this small portion of the love has been put in resonance, in emotional resonance with the Earth, and at the subsequent encounter, it can impact, as Giovanni also explained very well in his talk this morning. So if the condition is that this portion of the line of variation has to pass through a keyhole. Well, the third part of the title is an analytical approach. So we would like to make this analysis in a framework in which it's possible to make calculation and to have explicit equations. And the framework is exactly the same as the one used presented in Giovanni's talk, is the analytical theory of close encounters. So here I think I can go a little bit faster. So our tool will be the B-plane, which I recall is the plane passing through the Earth or whatever planet you want center, and is perpendicular to the unperturbed planet-centric velocity vector of the small body, which is approaching the planet assuming a hyperbolic trajectory. So our model is the circular restricted three-body problem, and with also the small body assumed to be without mass. And with further two assumptions. So the first is that when the small body is far from the planet, we neglect the perturbation of the planet, and we assume the trajectory to be an unperturbed Keplerian orbit around the Sun. Whereas when the small body is close to the planet, we have the encounter, and the encounter is modeled as an instantaneous transition from the incoming to the outcoming plane. So we essentially have this figure. So we have from the top, the small body traveling along the asymptote of the hyperbola, and at the B-plane crossing, we have the rotation of the velocity vector u into u prime, and the small body is going away from the post-encounter B-plane. So here I also show two relevant quantities which I will use later, which are the impact parameter b, which is the distance at which the small body crosses the B-plane from the Earth center, and also the deflection angle gamma, which is the angle by which the vector u is rotated by the encounter. Well, so as a few remarks here, the modulus of the vector u is unchanged, and this is essentially due to the conservation of the angular momentum. And whereas we have also a formula, an explicit formula, which we will use later for the deflection angle, which essentially depends on a constant c and on the impact parameter itself. Well, the geometric setup of the theory is to have this planetocentric Cartesian reference frame with the sun on the negative x-axis and with the y-axis pointing in the direction of motion of the planet. Then we identify the vector u by three variables. One is the modulus u, and also two angles, theta and phi, which are shown in the picture. So theta is the angle between the y-axis and the vector u, whereas phi is the angle between the yz plane and the plane containing the vector u. And the other quantities we will look at in what follows are the B-plane coordinates xi and zeta. Well, despite their formal definition, it's most important here to give the dynamical interpretation of these quantities, because they are related to the, let's say, to the two most important quantities to look at when studying close encounter. So the coordinate xi is the local mode, whereas the coordinate zeta is related to the timing of the encounter. So the first coordinate tells how close the two orbits, that of the small body and that of the planet, can be, but it's just a geometric property, because there is no need that the two bodies are at the moid point at the same time. So the second coordinate becomes more relevant here, so because it measures, in some sense, the timing at which the small body arrives at the encounter with the Earth. So, well, now I can go in the details of our study. So first, we have to introduce a model for the line of variations before to study, of course, its evolution due to a close encounter, and we used the so-called wire approximation. So in this approximation, we assume to have a set of small bodies all traveling along the same trajectory and spread along the trajectory in mean anomaly. Of course, this is an approximation, but it's, as also Giovanni discussed this morning, it's a good approximation because the asteroid orbital uncertainty implies small differences between the virtual asteroid and semi-major axis, and in turn, this difference, especially when propagating orbits, accumulates mostly in mean anomaly. So, if we assume this approximation, we have the line of variations on the B-plane, as represented in the figure, as a vertical straight line. So we have xi equal xi0, and the difference between the small bodies is in the zeta coordinate, because it's the coordinate related to the timing of the encounter. Whereas since all the small bodies travel along the same trajectory, of course they all have the same local mode with the Earth or with the planet. Well, so this is our model for the line of variations, and these, of course, you have not to look to the detail of these equations, but we will come back to some of them later. Anyway, these are equations that allows us to compute post-encounter quantities, which are the quantities with a prime, as a function of the pre-encounter one. And of course, in these equations, we substituted xi with xi0 because we would like to compute post-encounter quantities corresponding to points along our line of variations. Well, the first thing we looked at is the post-encounter local mode, which is Xi prime. So before looking at the result, I will come back to the equations, in particular to equation 5, to make some remarks. So, well, since theta and theta prime varies between 0 and pi, we have that the sign of Xi prime is the same as Xi0. So the post-encounter local mode is has the same sign as the pre-encounter one. And second, which is actually a quite obvious fact as a physical interpretation, but we can look at it also from these equations. If you take equations 1 and 2 and you let zeta tends to plus or minus infinity, you can see that theta prime tends to theta. Well, if you remember our wide approximation, large values of zeta corresponds to be far from the planet. Thus, the encounter has less and less effect, and this is why theta prime tends to theta in this case. But in this case, equation 5 implies that Xi prime tends to Xi0, so essentially the post-encounter local mode is the same as Xi0. Whereas for smaller values of zeta, we expect a variation in this coordinate Xi prime, and in particular we expect maximum and a minimum at least of this point. And this is exactly the content of our first result, which is the following. So we have two extremal values for Xi prime correspond along the wire, of course, corresponding to the two values of zeta, zeta plus and zeta minus, and these two critical points always exist. Additionally, if Xi0 is not too large in absolute value, there are an additional two critical points, zeta 1 and zeta 2. Well, I also put here some details of the proof, but not to explain it in more detail, but just because in the second part of it, we have also the possibility to have more insight in the equations. So the idea is very simple, actually. We computed the derivative of the sinus of theta prime, which is the quantity involved in the equation for Xi prime, and this derivative has two factors. The first one is this derivative of cosinus of theta prime with respect to zeta, and when we equate it to 0, we obtain a quadratic equation giving us the two values zeta plus and zeta minus. Very simple computation. The other factor, relevant factor, is cosinus of theta prime. Well, when we equate this factor to 0, this is equivalent to fixing the post-encounter value of theta prime, which in turn is equivalent to fixing the post-encounter semi-major axis. And thus, recalling also the talk by Giovanni, we are considering a circle on the p-plane. Circle whose center is on the z-axis. And thus, to obtain the additional two critical points, we simply have to look at the intersections between our vertical line with this particular resonance circle. And this also explains why Xi0 cannot be too large. In particular, it cannot be too large in absolute value than the radius of this circle, of course. And this gives us another quadratic equation and the values of zeta 1 and zeta 2. Well, to now look at how this formula work in practice, here there is an example of the 2017 encounter of the 2012 TC4. Well, this is the corresponding B-plane. The circle is the Earth cross-section, which means the Earth with radius accounting for the gravitational focusing. And we considered two different line of variations, which are the two vertical lines in black here, which are Xi0 equal -4 and Xi0 equal -2 in Earth radii. Well, the red and blue curves are the post-encounter globes, so are the post-encounter line of variations. And you can appreciate here that these vertical lines have been deformed by the encounter, of course. And for instance, if you look at the red line, you can okay, you can see that about this point you have the maximum value of xi prime, which is the coordinate on the horizontal axis, whereas in the right part of the red curve you have the minimum value of xi prime. The minimum, of course, in absolute value. And from the situation is similar, but not the same for the blue curve, because even if it's not so much, it cannot be so much appreciated from the blue curve, but in the right part of the blue curve there are 3 critical points. So this vertical line corresponds to the case for which we have 4 critical points, 2 minimum and 2 maximum points for xi prime. So here, of course, there is one of these critical points, and the other 3 are located in this part. But this will also be more clear in the next slide, because I want to show the same figure, but with additional B-plane loci to better understand what is going on here. So the Chan hyperbola, which also Giovanni showed, is the condition derivative of cosinus of theta prime with respect to zeta equals to 0. So the points at which the vertical lines, our line of variations, intersect this hyperbola corresponds to the value zeta plus and zeta minus. So here for the left line of variations, we have the intersection with hyperbola, these 2 intersections corresponding to the 2 critical points, which are only 2, because the other 2 points are given by the intersection with this circle. So this circle is the resonance circle I was mentioning before, which is the one corresponding to the condition cosinus of theta prime equals to 0. And you can see that the other line of variation, so the xi0 equals -2, intersects both the hyperbola and the circle. So we have, this is a case for which we have 4 critical points, and one is in the left part of this blue curve, and the other one is the other 3, sorry, are on the right part, on the right portion. Well, so this confirms, is an example of our result, and we also here compared. I don't have the figure, but we compared as in the example of Apophis by Giovanni. We compared these, which are analytically computed points, with points resulting from numerical integration of the problem, and we have a very strong agreement here. Okay, well, I can now pass to the last part by focusing on the post-encounter velocity. The post-encounter velocity, so u prime. So a few remarks here again. Well, first, as I was mentioning at the beginning, the modulus of u prime is preserved by the encounter. Thus, whatever u prime, the vector u prime is, its modulus is u, and thus all these u prime vectors are located on a sphere of radius u, which I will call u sphere in what follows. What we are interested in is to understand what is the distribution of these u prime vectors. So what are the accessible post-encounter velocities for orbits along the line of variations in our theory, of course. And here I have 2 remarks. Well, from the point of view,
you have 10 minutes left, including the 10 questions.
Okay, thank you. And okay, from the point of view of the deflection angle gamma, if you recall the formula C over B, we have, and this is again, if you think at its physical interpretation, an obvious fact that if we let zeta tends to plus or minus infinity, this gamma tends to 0 because the encounter has a negligible effect. And in turn, the maximum deflection occurs at zeta equals 0 because it's the closest point to the planet along the wire, and the angle gamma max, which is the maximum deflection, is given by this expression. But another thing we noticed is that if we considered the post-encounter velocity vectors u prime corresponding to the 2 points along the wire for which we have the critical points, so for which we have the maximum and the minimum of zeta prime, of C prime, so the points zeta plus and zeta minus I was mentioning before, we obtain two vectors, as I can show you in this figure. We obtain two vectors, u prime plus and u prime minus, which lie on the same meridian on the U sphere. So they both have the phi prime value. They both have the same phi prime value. If we compute the difference in the other angle, so in theta prime, we obtain, as you can see here, an angle which is the same as gamma max. So this suggested to us that the accessible values, accessible vectors u primes, can lie on a circle on the U sphere. And this is true, and we have this result. So the post-encounter values of the angles theta prime and phi prime accessible from small bodies along the wire is a circle on the U sphere. And in particular, it's the intersection between the U sphere and a cone, whose vertex is in the center of the sphere, and whose aperture is this angle gamma max. Well, I can skip the details of the proof, but yeah, the idea is pretty simple. So we simply computed the midpoint between p plus and p minus, which should be above in some, let me say in this way, above the center of the circle, and we computed the distance from this point to the tips of u prime for points along the wire, and we saw that this distance was constant. Well, it's better, yeah, to have a visual representation of this. So this is again 2012 TC4, and this is the U sphere. So it's the sphere with radius equals to the modulus of the planetocentric velocity of the asteroid, and the green circle you can see here is exactly the circle I was referring to. So it's the tips of the vectors u prime for points along the wire has to lie on this circle. In particular, I would like to note that the vector u is one of these points, and that's because this is the first remark I did. So when zeta tends to plus or minus infinity, basically the encounter has no effect. So u prime is equals to u, or better, u prime tends to u, and thus you can see the circle as a sort, so to speak, of compactification of the line of variations, at which the points at infinity, so for larger values of zeta in absolute value, corresponds exactly to this point identified by the vector u. So well, this was the last thing I would like to say. So thank you, and I can take question now.